Hey there everybody! The purpose of this video is to walk you through an algebraic proof to question E9 in the variation homework. This is kind of a tricky one potentially. It says if you take a bunch of data points and you double them all, what happens to the standard deviation? Now in the center homework, we remember that if you take a bunch of data points and double them all, the average is doubled. So it's very easy to just say, okay, if we take a bunch of data points and double them all, the standard deviation is also going to be doubled. But there's no real reason to believe that that's necessarily true. You can totally witness it for this particular data set right here by running it through your TI. But what I want to do today, and if you're not into algebra, you might want to just turn this off now, because this is going to be an algebraic proof of if an original data set has an average of x bar and a standard deviation of s, why, if you double all the data, the new data set, which we already showed has an average of double x bar. We're going to assume that, and if you want to see a proof for that, go back to the previous homework. Why the new double data has twice the standard deviation. Now, logically, and we can reason through this, if all the data is twice as far away from zero as it used to be, that means all of its distances are twice as far away from zero as it used to be. So that logically makes sense as to why it should double. But in case some of you want more of a rigorous proof, that's what I wanted to do for you today. So, if you remember the definition of standard deviation, okay, the standard deviation, this is the original data set. In general, it's going to be the sum of all of the squared deviations from average divided by n minus 1. And it's radical. The whole thing's radicalized. So what I want to show today is why the doubled standard deviation looks just like this, but there's going to be a 2 out in front. That's what I want to show. If I double every single one of those, it's going to look exactly the same as this, but there's going to be a 2 out in front of that radical, which will mean that it's doubled. Okay? So wish me luck. What is the standard deviation of the doubled data going to look like? Well, we know by definition, it's a big old radical. It's a big old radical. Each data point, which remember now, each of those data points is doubled. So it's going to be 2 times x sub 1 minus the average, which is double x bar squared. The next data point is doubled x2 minus 2 times x bar squared. And this is going to continue all the way down the line until we get to the last data point, 2 sub xn minus 2 sub x, or 2x bar, that whole thing squared. And we're going to divide the whole thing by n minus 1. Cool so far? Cool so far. All right. Now here's where the algebra comes in. What I do not want to do at all in this computation is multiply this out. So we're going to use a little bit of algebraic cleverness. Each one of the two terms in this binomial have a factor of 2 squared. Okay? You can, if you will, you can do a distribution, and this is getting a little algebra-y, and my board isn't quite big enough to do it out step by step by step. But really, each of these things, if you were to multiply these out, FOIL them if you will, you would see lots and lots and lots of 4s. 2x sub 1 times 2x sub 1 is 4x sub 1 squared. 2x bar times 2x x sub 1 is 4 x bar x sub 1. Lots of 4s. So what I'm going to do is, and the same thing happens in every single term, I'm going to pull those 4s out of each one of those terms. So you're going to be left with 4 times x1 minus x bar squared plus 4 times x2 minus x bar squared. Going all the way down, 4, oops, plus 4 xn minus x bar squared. That's all over n minus 1. Some of you might need to vomit right now, and that's totally fine. Go ahead and do that. But now, we got something special going on. Because now each of these terms in the larger overriding construct also has a factor of 4. And that's totally rad now, isn't it? Because I can pull that 4 out. 4 times, I'm going to use brackets and parentheses, x1 minus x bar squared plus x2 minus x bar squared plus dot 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 xn n minus x bar squared all over, let's put a bracket on that, n minus 1. If you have to vomit again, go ahead. We're almost done. Now notice that that 4 that's right there, that 4 right there also has a perfect square root. So I can pull that 4 through the radical because the square root of 4 is 2. So you're going to end up with 2 times the radical of all of this. x1 minus x bar squared plus x2 minus x bar squared plus dot 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 xn minus x bar squared all over n minus 1. And then you know we're done now, because this whole quantity right here is simply the standard deviation of the original data. It's the sum of the squares of all the deviations divided by n minus 1 and radicalized. So it's equal to 2 s's, which brings us right back to what we wanted to show in the first place, was that the sum of the doubled data deviations from their average is simply equal to twice the deviations of the original data. Boom. There we go. We got it. We got it. Hopefully that makes perfect sense. If it doesn't, and like I said, I'm never going to actually give you this on an exam. It's a very, very kind of tedious algebraic justification. But it shows not just for that particular data set, but for any data set. And here's what's kind of cool. If you change that 2 to any other multiplier, this exact same logic works. Because think about this. The only reason this is 4 is because it's 2 squared, 2 squared, 2 squared, 2 squared. If this was a 3, this would be a 3 squared or a 9. If it was a 1.5, it'd be a 2.25. So it doesn't matter what multiplier you end up using, the same result happens. If you multiply any data set by a fixed constant, the resulting data set has to have a standard deviation that is completely related to the original standard deviation by being multiplied by that constant. There you go. Hopefully that makes sense.